Hello and welcome to another video in this series as we journey from the very simple primes to the foothills of the Riemann hypothesis. Today we're going to be looking at quite an interesting challenge, and that is trying to understand the growth of the prime harmonic series, that is the sum over the inverse primes. Let's get started. So previously we've seen that the harmonic series 1 over n, the sum of those diverges. Now initially that was a little counterintuitive because each of the terms is getting smaller, but we did show that actually it diverges. The sum does actually get ever larger. We also used integral comparison to show that the partial sums grow like log n. Worth going back to look at that video because it's a really nice, simple but quite powerful technique where we're comparing an arithmetic function with a smoother function and using calculus integration to compare the area under a curve with this discrete sum. And it's used a lot in number theory, definitely worth knowing about, and as I said, it's not difficult at all. So 1 over n diverges and 1 over n grows kind of like log n. That means that as n gets larger, this gets closer and closer to log n. Now we are interested in the primes, perhaps more than the normal counting numbers, so we looked previously at the prime harmonic series, and we also showed that that diverges, and the proof was just a little bit more lengthy, but still accessible, and definitely go back and have a look at that. So that divergence, in fact we showed two proofs. So if you look at the YouTube channel you'll see a very accessible simple proof, but also a quicker proof that just needs a teeny bit more mathematical kind of comfort. But both are generally accessible, and we show that the prime harmonic series diverges as we kind of the sum gets extended to all the primes. Now that was interesting because what it says is that although the primes get further and further apart in some sense, there's less and less of them, there's still enough of them to make the sum diverge. If we compare that to the inverse squares, 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, those really are far apart, and we can prove that that sum of inverse squares converges. There's not enough of them, they're not dense enough to make it diverge. So that's interesting. The question we haven't asked yet is, how does it grow? We know it diverges, but how does it grow? Does it grow in some similar way to log n? Our initial thought, if we were kind of just making an educated guess and new to this field, we might actually have said that this grows like log n, perhaps because it kind of does get larger, the sum, but it slows down. But actually this one does. So in some sense this has to grow slower than that. But what's the nature of that difference? Is it a constant difference? Is it a factor? That'll be interesting to find out. In fact, Euler made an assertion around this. He thought he'd proven it. He said the sum of the reciprocals of the prime numbers, these things here, is infinitely great, but is infinitely times less than the sum of the harmonic series. And the sum of the former is as the logarithm of the sum of the latter. Now, he wrote that in Latin, so it's subject to some translation, but generally we conclude, we kind of agree, there's consensus about what he means, and he's saying that both series diverge, and it's infinitely great, But in some sense, he's saying that the sum of the reciprocals of the primes is smaller. He calls it infinitely times less than this infinity. Now, we're playing with infinities here, which is always an adventurous, unsafe thing to do. But his sense was that this infinity was somehow smaller than this one, or the growth of that series was somehow less than this one. And he expressed it by saying it's the logarithm of the latter. So we can write that down in modern language. We can say the sum of the inverse primes, the finite sum, not the infinite sum, for p prime less than or equal to x. So prime's up to a number, so we cut off the series at some point, grows like log x. So log x was how the harmonic series grows, and he's saying that actually the prime harmonic series grows log x, so log of that. That's what he's saying. He was actually right, but his proof was doesn't meet kind of modern standards. He was very intuitive in his the paths that he followed, and very often they were right, but we can't accept them today. And for the main reason being that we can't play with infinities in the way that he did, because it leads to inconsistencies. It is definitely fun and interesting to go and look at his original work. This is just a little capture from his work. You can find a scan of the original publication online. Here's a link, and it's really fun to kind of try and decode what he said. So let's try. I don't speak Latin, but theorem 19, summa serii reciprocae numerorum primorum, the sum of the series of the reciprocals of the prime numbers. And he's written them out, and he's written etc., which is a Latin Latin word. Est infinite magna is infinitely big. Infinities tamen minor, but infinitely times smaller, minor, smaller, less, quam summa serii harmonicae, than the sum of the series, the harmonic series, which he writes out. Atque, that might be similar to Spanish aunque, although the sum is something logarithmus. It's quite fun to do that. If you speak more Latin than I do, that's a fun thing to do. Right, let's dive in. And it took me a while to make this video, because most of the proofs out there that show how the prime harmonic series grows are a little complicated and a little difficult, and I wasn't really 100% happy with them. What I did find was Paul Pollack's short paper, a proof, and he came at this problem by trying to understand how Euler could have done it using methods available at his time, so nothing too advanced. And the proof actually it works in the sense that it doesn't require advanced knowledge, so it's perfect for where we are in our learning. It does require a bit of bookwork, unfortunately, so there's, between each step there's a bit of algebra that we have to do. So this video is not going to just read that paper. If you are very comfortable with mathematics, go straight to his paper, and it's fun to read. If, however, you would like a walkthrough, step by step, going slower than his paper, trying to understand how he gets from one line to the next, this is what we're going to do in this video. So that's the point. And also what I'm going to do is I'm going to give a helicopter view of the strategy of the proof before we dive in. I do find a lot of maths papers don't do that, and you kind of follow a trail and you're not really sure why or where it's going, I think it's really useful to be able to paint a broad picture first, a plan of attack, before diving into the details. So this is a proof overview, and the idea is, well, we're focused on this thing here, aren't we? We're focused on the sum, the finite sum, the sum of the inverse primes up to a number, up to p less than or equal to x. So not all of the primes, just all the ones up to a particular cutoff point. And we want to find some expression that describes that. And our approach will be to find something else that equals that we can work with, because this is actually quite hard to work with. This other thing is what we're going to work with, because it will allow us to find related objects. So let's call this sum 0 or sum p. We're going to find some upper that is more than or equal to this, and a sum lower which is less than or equal to that. That means these are upper and lower bounds, and these things will hopefully pop out as being really simple expressions. Hopefully, maybe log x plus or minus some constant. In fact, they will. So this thing is harder to work with, but we will find an equivalent expression, which initially will look more complicated, but actually the payoff is that it allows us to find lower and upper bounds. Let me draw that as a picture, because I think visual kind of explanations are always helpful. So we are interested in the sum of 1 over p of p less than or equal to x. That's hard to work with, so we're going to find something else that is equal to that. And this thing will actually have a general form, and we will find another form which is always more than or equal to that, and another lower form, SL, which is less than or equal to that. So that means this will be an upper bound, this will be a lower bound on the prime harmonic series as it grows. That's what we're going to do. So that general form is this, and it looks scary, doesn't it? It's like, whoa. But bear with us. It's not actually that scary once we stare at it for a few seconds. So this general form of this sum, now you might say, hang on, where did this come from? And actually it does take a lot of work and research that others have done. So I'm not exploring how this came about, but somebody managed to find it, and actually it's been really helpful. But let's look at it. So this thing is simply p raised to that power minus 1 of log x, and you can rewrite that in fractions and other forms, but that's all it is. P raised to something multiplied by another function where we feed it parameter p minus 1 over log x. So this s, this sum, this more general sum, is a function of a function. Yes, it takes a variable x, but it takes another function, this one here. So it's a function of a function. That's not too complicated. You know, we can do that. So this more general sum is a function of this lambda. Let's pass it t, and we're going to say that t is defined only over 0 to 1 inclusive. That's just the way we're going to define it. You'll see why in a minute. So that's an easy thing to do, nothing too advanced there. To motivate you sticking with this thing will collapse into simplicity, and out will pop the nice results that we're looking for. So that's the promise. That's why I think you should stick with this. Now, if that lambda function is of this form, 1 over t, but only if t is from 1 over e to 1. If it's less than that, it's 0. So we've defined this function. It's like 1 over t. It's like, 1 over x, 1 over t, but not quite. We're actually going to chop it off at this point, 1 over e. So this is a function lambda naught that we're interested in for now. And again, you might say, why? And the promise is that everything will just nicely cancel out into something really useful and simple. So remember, lambda is defined from 0 to 1, so it's not going to be larger than 1, it's not going to be less than 0. But within that, we can choose what function it can be. It could be t squared, it could be 1 minus t, it could be sine t, but we've chosen to have it of this form. Right. Why? Why is that cut off at 1 over e? Let's see what that range means. 1 over e less than t less than 1. That's this range here that has values that aren't 0. So this will contribute. So if you look back at that sum, if this is 0, then the whole thing here is 0, which means it contributes nothing to the sum. So when this is non-zero, that's when it contributes something to the sum. So so we need to explain why we chose that 1 over e. So let's see what that means. 1 over e less than t less than 1. And t is of the form p to the minus 1 over log x. Remember we said that at the start? That was how we defined that more general sum. We can take logs of this expression here. So the log of 1 over e is minus 1, log of 1 is 0, and the log of this is minus 1 over log x log p. Multiplied through by log x is minus log x is less than or equal to minus log p, less than or equal to 0. So raising, actually you can just by inspection you can say actually 0 is less than p is less than x. These manipulations are only possible if this log function is monotonically growing. If it was a funny function like sine, we couldn't do that. So 0 is less than p is less than x. Well, actually that's what we're interested in. We only want to sum over p if it's less than x. So by applying this constraint, that's the same as saying 0 is less than p is less than x. So that means that sum is only really going to be over p less than or equal to x. If we actually looked at the other range, 0 to t to 1 over e, where our lambda is defined as 0, then it leads to, if we did a similar kind of algebra there, it'd lead to x is less than p, as in p is more than x. So p greater than x all the way up to infinity, and actually for that range it contributes 0. So that's nice, that's what we want. Let's summarize what we've said. Our choice of that lambda means that as we do this sum, the only contribution this will make to the sum is when p is less than or equal to x, which is what we want. If p is more than x, this is 0, and therefore there is no contribution. So that's nice. Takes a little bit of bookwork, but that's nice. So that definition that we chose for lambda naught reduces that sum as we promised. Let's write it out. That sum, with our particular choice of lambda 0, we've just written out the definition here. Now we've said lambda of t is 1 over t in this case. Remember? Here, 1 over t in this case, which is p plus to the power plus 1 over log x. It's just inverted this. P to the plus 1 over log x, when we multiply it by this one here, those cancel out because the exponents are added, which leaves just p minus 1. The sum of primes, the inverse primes, for p less than x. That's what we want. So what we've shown, that's a fair bit of algebra there, but we've achieved our first phase of this proof, which is to find an object, kind of a general sum here, which actually for a chosen configuration reduces to the sum we're interested in, which is the prime harmonic series for p up to and including x. That's this one here. So we've done that. Great. So that's nice, isn't it? But you might say, that was a lot of work. And we're doing this all because just working directly with this 1 over p and writing it out, it doesn't yield results as easily. Working with this thing, despite initially being a little bit more algebra, does turn out to be useful. So let's now proceed to the next phase of this proof. Now we're going to look at another form for lambda, and a very simple form. It's just a linear form, a straight line, alpha plus beta t. This is linear, really simple. Before we proceed, let's see what happens when we do pop that in to that general sum. So the definition is here, and into lambda, well, it's of this form, isn't it? So it's alpha plus beta times t. T is the parameter that's passed to lambda. And we can expand out this, so it's a times that and this thing times that, so it's just writing this out. Now you might say, hang on, where does that p come from? Let's look at this, just one of these here. So we had the sum over p of p to the minus 1, p to the minus 1 over log x times alpha plus beta t, which here is p to the minus 1 over log x. And then we can multiply this out and this out, equals sum over p minus 1, p minus 1 over log x times alpha. That was easy. Plus, that's going to be beta, p minus 1, p minus 1 over log x, p minus 1 over log x. And there's two of those, so that becomes 2. Now if we say ps is the sum of 1 over p to the s, this thing here is actually p, it's actually 1 plus 1 over log x. So it's almost the general prime, it's almost like a prime zeta function. We can call it that, we can call this a prime zeta function, where s is what p is raised to. And this thing becomes p 1 plus 2 over log x. So that is why we've written it in this form. So it's a prime zeta function. Great. So this is what we arrive at for the general sum if lambda is a linear function. Now we need something to help us with these expressions, which are the prime zeta function, which are of the form 1 plus something. We need something to help us with that before we can continue. Now this is a point in the proof where we're going to pause this attack, go sideways and do a little bit of algebra again to help us find something that can unlock these, and then come back. So if you want a cup of tea now or a coffee or something, take a break. We're going to go sideways, do a little bit of algebra, bit of bookwork, develop something that helps us unlock this, and then come back. Great. So we're actually going to develop 3 results that get us there, 3 interim results. I think the maths papers call them lemmas, or proposals, or other things like that, but we'll just call them interim result. First result, second result, third result, just to keep the language simple and friendly. Right, let's start with the first one. So to remember, this is the phase where we're just preparing some results which will help us unlock that, unlock this thing. That's where we are. So we'll start again with the Euler product formula, the golden bridge, which is the Riemann zeta function, which we know is 1 over n to the s, and it's that product there. If we take logs of both sides, taking logs is a natural thing to try and do whenever we see a product, because it turns a product into a sum. It's valid as long as s is more than 1, as in this thing is not infinite. We can't easily take logs of infinite things. So we can say the log of the zeta function is this product turns into a sum. There's a minus 1 here, so that becomes minus. Actually, let's write that out. So we have the log. Actually, in number theory they seem to use log rather than ln for just convention. So we have the log of the product of 1 minus 1 over p to the s minus 1. And we know that the log of a to the b is the same as b ln a. If that's minus 1, that's minus 1. That means this can come out the front. So that becomes ln, so there's a minus 1 there, the product of 1 minus 1 over p to the s. And we also know that the log of ab is the log of a plus the log of b. And if it's abc, then it's log of a, log of b, log of c, and so on. So this product becomes a sum equals minus the sum of the log of 1 minus 1 over p to the s. There you go. That's what we've done. There you go. So actually these kinds of things become very kind of natural for professional mathematicians. They kind of don't need to explain what they've done, but for mere mortals like myself, that can take a little bit of a reading to understand how did that jump happen. Right, great. Now we've got this thing here, 1 minus 1 over p to the s, 1 minus something. We can use the power series expansion for log of 1 plus x, which is x minus x squared over 2, and so on and so on. These are standard things you do in school, and it's valid for x being the absolute value being less than 1, which is the case here, because if it's 1 plus the prime, 1 over p to the s, that's always going to be less than 1, even if we've got a minus sign there, because it's the magnitude. So we can use this, and remember the general term here is going to be, if this is 1 minus x, this is going to be minus x squared over 2 minus x cubed, so it's all minuses. So that all those minuses, because there's a minus out here, becomes a plus. And the general term is x to the n over n, which in our case is p to the k divided by k. If you're not convinced by that, let's write that out. Remember, this video is about explaining all those steps. If you're very happy with this, you can just go straight to the paper that goes through much more quickly. So we're going to use log 1 plus x, which is saying that it's x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, and the general form is x to the n over n minus, and this yeah, it alternates, doesn't it? And if we said log 1 minus 1 over p to the s, well, actually let's do an intermediate one. Log 1 minus x equals minus x minus x squared over 2 minus x cubed over 3 minus x to the 4 over 4, and so on. So they're all minus signs now. So if we say log 1 minus 1 over p to the s, it's minus, so actually the general form here is minus n, so x to the power n over n. That's the general form. So if we're using 1 over p to the s, that's going to be the sum, if we use k instead of n just to keep it clear, minus, now x is 1 over p to the s raised to the k all over k, that's just this thing here, equals, take the minus out, sum over k of 1 over k p to the sk. That is this thing here. So again, a lot of algebra behind these steps, but that's the point of the video, is to go through it. So we can now say that the log of the zeta function, remember it was the sum over primes, over the log of 1 plus that expression, this thing here, which becomes the sum over k of these forms 1 over k p to ks. Now remember, k is going from 1 upwards, 1, 2, 3. If we just separate out k as 1 and have the rest as k more than 2, we've just split it into 2. K is more than 2, more than or equal to 2, and k is 1. In that case, that's just the simple prime harmonic series 1 over p to the s, because k is 1 summed over primes, so that's ps. So we've just split the case where k is 1, we've just split that out, and then left with this bit. Now you might look at that and say, you might say, yep, that definitely converges, because it's of the form 1 over something where the power is more than or equal to 2, and we know from previous work that when 1 over x to the s, or x to the n, when n is more than or equal to 2, those series converge, like the Basel problem. But let's do it properly. Actually, this is interesting, isn't it? We've got our p to the s out. That's interesting. Now let's look at this thing. Again, it looks complicated, doesn't it? But let's look at it and say, well, s is more than 1 and k is more than or equal to 2. In which case, if k, let's look at the general term, if k is more than or equal to 2, this thing is always going to be less than 1 over 2 p to the k. Let's write that out again, it's easier to write it out. 1 over k p ks, and we're going to compare that to 2p to the k. Now we've said that s is more than 1. If s is more than 1, then it means this denominator is bigger than this one, which means that is less than or equal to this thing. In fact, it's less than, because we've said here s is 1. We can also say that because k goes from k is more than or equal to 2, k could be 3k, it could be 4k, it could be 5, which means that this denominator is bigger than just k is 2. So we put 2 there. So there's 2 steps in one there to say why this is always less than that. So that means this complicated expression is less than or equal to half sum over primes, sum over k, 1 over pk, because we managed to remove the reference to s and that k at the bottom there. So it's between 0 and this upper limit. You might say, well, how does that help us? Let's step a bit further and you'll see why. We're going to make use of another power series, which is this one. 1 minus x to the minus 1 is 1 plus x squared plus x cubed, and so on. Again, it's a common school kind of identity that we learn. It's easily proved. So we can use this to say well, actually, let's write out what we've just shown. We've shown that that complicated expression is less than or equal to half sum over p, sum over k more than or equal to 2, 1 over p to the k. If we write those expressions out, k is 2, k is 3, k is 4, that starts to look like this power series if we factor out p. So we take out a p, 1 over p, so what's left in the bracket is 1 over p squared, 1 over p cubed, which is almost this except for that 1. So if we take 1 from this, we're left with that. So it's 1 minus 1 over p to the minus 1. Take away 1. That's making use of this. And this thing you can write really, you can just rewrite that as 1 over p minus 1. I won't do that because that is actually really easy. If it isn't, get back to me in the comments and I'll show you. Phew. Great, we're getting there. So actually that thing, that complicated bit, is less than this. Now let's look at that again. The primes are a subset of the counting numbers. That means if we replace p with n, this is going to be less than that. So this thing over the primes is less than the same thing over the normal natural numbers, because there's just less primes than normal numbers. And this thing, we're getting there, don't worry, we're almost there. This thing, 1 over n minus 1, is actually 1, and there's a half here, which makes it half. Now, you might say, why is that? Well, this fraction can be rewritten as 1 over n minus 1 minus 1 over n. Let's show you why. So let's write that down. 1 over n minus 1 minus 1 over n. And to subtract fractions, we have to make the bottoms the same. Just basic school maths that we've done. So to do that, we multiply top and bottom by n minus 1 equals n minus 1, oops, that's a minus, over n minus 1. Bottoms are the same, so we have n minus n plus 1 over n minus 1. N's cancel, so we're left with 1 over n minus 1. Now there is a way of getting from there to there, but I just wanted to show you that was equivalent. Now actually, let's see what happens when we write that out. Let me choose a different colour. If I write that out, and we start with n is 2, so that's 1 over 1 minus 1 over 2, and the next bit is plus 1 over 2 minus 1 over 3, plus 1 over 3 minus 1 over 4, and so on. Can you see what's happening? These cancel. So everything will cancel except the very first term, 1. That's why the sum, starting at n is 2, is 1. Because all those terms cancel except the very first one. I think it's called a telescoping sum. Phew, right. So that means the difference between the log of the zeta function minus that ps, which is that complicated sum here. Remember, so log of the zeta function minus this leaves this, and we've just shown that this thing is less than a half. That's our first result. Phew. You might say, wow, what use is this? But it'll get us to unlocking the main path on our proof. It's an interim result. By the way, this is not the prime harmonic series, because that would mean S is 1 and that diverges, so we can't make those kinds of conclusions. Right, let's move on to our second interim result, and I promise you this is super simple. It's just this slide. We have actually done the work before, so in that previous video where we did the integral comparisons to compare continuous functions with discrete functions, we did actually arrive at this result. So I won't repeat it, you can go back and do that. And we said that the zeta function, zeta of s, is between 1 over s minus 1 and 1 over s minus 1 plus 1. It was actually a really easy result to find. Again, go and have a look at that video or the blog post. But we can just rearrange this by multiplying all of it by s minus 1. Remember, s is always more than 1, so that's fine. So that means 1 is less than s minus 1 times the zeta function, which is less than s. And that's our second interim result. We're going to use that later. Now on to our third one. So, again, take a little pause if you want at this point, and then we're at when you come back, you can start this third final interim result before we get back to our main proof. So, this is the first result. So in this third result, we're combining the first and second results. So let's start from the first result. We said before that the log of the zeta function minus the prime zeta function, the difference, one minus the other is less than a half. It's between 0 and a half. If we said that actually s is going to be between 0 and a half, we'd have to rewrite these to adjust them so they become valid again. Because remember, these are only valid for s is more than 1. So we could do s plus 1. If we rewrote s as s plus 1, we can say p s plus 1 and the log of zeta of s plus 1. Now we can say s is between 0 and a half, and you'll see why we're doing that in a minute. It's just a way of rewriting that now. And this is just rewriting this backwards, so instead of a minus b, we're saying b minus a, so we swap the inequalities around. So this is now saying that difference is between minus a half up to 0. Now let's take the second result and go forward with it. The second result, which for s more than 1 was this thing here that we saw. If we are, as we said, we're going to restrict s to be between 0 and a half, we need to rewrite that with s plus 1. And it's easy to do. 1 is less than s plus 1 minus 1, which is just s, and then that s becomes s plus 1, and this s becomes s plus 1, and remember it's less than a half, so it's less than 3 over 2. Why is that? Remember, s, it goes up to a half, so s plus 1 goes to 1 and a half, 3 over 2. That's where that comes from. So this expression here is less than 1 and a half as long as s is in that range. If we take the log of that, 1 becomes 0, s times the zeta of s plus 1, the product becomes a sum, so it's log of zeta of s plus 1. And this thing would be plus log s, but if we invert s, it becomes a minus, and you'll see why we've done that. This is just a convenient form for later. So this would become log s plus log s, but if we invert it, it becomes minus log 1 over s. And the log of 3 over 2 is less than a half. You can even verify that numerically. We could show it algebraically, but that's just a number which I think is 0.4, which is less than half. So that's valid. Now we've got these two inequalities. We've got this one from the second result and this one from the first result. Notice they've got PS, they've got P and a log, and this one has got a log so that's a plus log in there, that's a minus log. So if we add them, those logs would cancel out. So if we add the two inequalities, we're left with ps plus 1 minus log 1 over s. And that goes from minus half up to plus a half. If you want to see how that worked, it's yeah, go on then, we are here to show it, aren't we? So the first result was minus a half is less than ps plus 1 minus log of the zeta of s plus 1 was less than 0. Our second result led us to 0 is less than log zeta of s plus 1 minus log of 1 over s. And we said that was less than a half. So we can just add, we can say minus a half is less than, so that's adding those, and adding those will give us less than a half. This thing cancels with that, which leaves us with p s plus 1 minus log 1 over s. That's our result here, and you could write it more succinctly like this to say the magnitude of the difference is less than half, but we can keep that around because it'll be useful. And remember, s is restricted now to be in this small range only. So we finally arrived at something with p of the form 1 plus s or 1 plus something inside. Now we can go back to our main proof, because we've now found something that can help us unlock that expression that we had. Remember, we arrived at that generalized sum with expressions p 1 plus something, 1 plus something. Now we've got something that can help us there. Let's write that out again just to remind us and for clarity. That generalized sum, when we had lambda naught, it reduced to the partial sum of the prime harmonic series for p less than x. For lambda of a linear form, alpha plus beta t, it becomes this thing here, which is made up of linear combinations of p with the parameter 1 plus something and 1 plus something. Remember that s again is between 0 and a half. Now if s is between 0 and a half, that means this thing here, 1 over log x or 2 over log x, must be in that range. So this is the bigger one, let's do that. 2 over log x has to be less than a half. That means x is more than e to the 4. That's an easy thing to do. Actually, let's do it while we're here. So 2 over log x, we said that's going to be less than a half. So if you multiply both sides by 2, we get 4 is less than 1. Multiply both sides by log x, and log x is always positive for x is more than 1. That means 4 is less than log x. E to the 4 is less than x. That means x is more than e to the 4. That's when that is valid. So our result overall will only be valid for x is more than e to the 4. But that's okay. That number is dealable, it's manageable, and we can use experimental methods or other methods to show the same result for smaller x, but x more than e to the 4 is perfectly fine. It's not even that big. What is it? Let's do it. Calculator. It's 54.6, so it's we can easily verify the results for less than that. Right, almost there. So for the first p expression, which had p1 plus 1 over log x, we're using this inequality, this one here, to say minus half is less than p1 plus 1 over log x minus log x. The reason that's there is remember it was minus 1 over log of 1 over s, and s here is now 1 over log x, so that becomes log x. And the same thing for the other p expression, which had 2, and that becomes minus log x plus log 2. That's just algebra. We're just applying the inequality that we arrived at, the one that's going to help us with the p 1 plus something. We're applying that to that generalized sum, because that's got these two p expressions, this one and this one. So these two lines are referring to each p expression, this one and this one. In this one it's p1 plus s, where s is 1 over log x, and this one is 2 over log x. Now if we multiply by alpha and beta, and remember they could be negative, that means this is easy to multiply by alpha. If we just multiply by alpha, there they are. It means that this thing is going to be somewhere in the range minus alpha over 2 and plus alpha over 2, but it's the modulus of the alpha. Now for some people that's really easy to understand. For others, you just have to think through what difference plus and minus, positive and negative, would make. But you can see this is always positive, this is always negative, and it's at the most extreme end. This is the most negative it can be, the most positive it can be. And the same thing for the other expression with beta. Remember this one here, p, and we're multiplying them because this generalized sum has the alpha and beta. This is just the analogous expression. It looks complicated, doesn't it? But when you break down what's happening, the steps are easy. Now when we combine them, we add them, this plus this, we can say minus alpha over 2 minus beta over 2 with the moduluses, the magnitudes. Same on this side, gives us that. And the middle bit, phew, it looks big. But actually alpha p with that first s plus beta p is just sigma, or not sigma, the generalized sum. It's this. The generalized sum is alpha p, beta p with the two different s's. It's just that plus that, which is that. Minus log x minus, so those things are in there. We just need to tidy that up a little bit now. Almost there, almost there. So let's deal with that, this kind of errant beta log 2. Now beta log 2, if we want to take that out, if beta is positive, it means we reduce the magnitude of this thing. If beta is negative, by taking it away, we've increased the magnitude of this thing. That means if we add the magnitude of beta log 2 to this side and this side, this still will be within that range. So we've added log 2, but the magnitude of beta, and log 2, it's gone off the screen there, magnitude beta. So that's still valid, that inequality. Now lambda 1 is alpha plus beta, so we can just simplify that as lambda 1 log x. There it is. Whew, we're doing a lot of inequalities here. It is worth it, don't worry. So we're saying that this, the generalized sum, minus lambda of 1 log x is between these two expressions, which are symmetric. So we can say the magnitude is less than alpha over 2 plus, I won't read it out, but you can see visually what they are. That's going to help us. We're almost there. Now that is the general form. That's true for any lambda where a lambda is of a general linear form, alpha plus beta t. That's all we assumed. So this is going to be true for any linear form of lambda. Now let's pick two particular lambdas that are linear, and they're specially chosen. By the way, we're at the last stage of this proof now, in case you're wondering. This is probably a good time to take another coffee. We're in the final stretch now, so you're almost there, the final phase. So we have chosen two linear forms for lambda here, lambda u for upper and lower, and we'll see why they are upper and lower. They are linear because it's something times t plus something, and something times t plus or minus something. So alpha here is e plus 1, and beta is minus e, and so on. And remember, this is just a nice property that we will use. Alpha plus beta is 1 here, so if we add alpha beta here, e plus 1 minus e is just 1. Same thing with these fractions. Right. Let's visualize those linear forms. Remember, this was lambda naught that we first had, and using that in the generalized sum gave us what we wanted, the partial sums of the harmonic primes for p less than or equal to x. That's this blue thing. Lambda u, the upper limit, is specially chosen to be more than or equal to lambda naught. It's always a more than or equal. And the other one, the lower lambda L, is always less than or equal. It's equal because it touches at these points here. So 1, 1 and 1 over e, they touch. So lambda L is less than lambda naught, which is less than lambda u, actually less than or equal, in that range, 0 to 1. That's a visualization, so you can see what's happening, and the important property of them is that they are more than or less than. They are bounds, upper and lower bounds for lambda naught. Since lambda u, the upper one, is more than or equal to lambda t, we can say that the sum which uses that lambda u is more than or equal to the sum that uses lambda naught, which actually, usefully, is that partial prime harmonic function, prime harmonic series. We're getting there. You can see now this thing is an upper bound to the series we're interested in. Let's write that down. So saying this is more than that is the same as saying, you know, that thing is more than this. So log x plus alpha over 2 and beta 1/2 plus log 2. Remember, this comes from the generalized sum, this thing here. We are using this right hand side. We're saying that sum, which is using our linear lambda, is less than, we've just put this onto the right hand side, so s of lambda u is less than lambda 1 log x plus this. It's actually a constant, isn't it, because alpha, beta and constants. So we're just using the right hand side of this. And we can replace the alpha and beta with the actual values, e plus 1 and e. and E being the constant 2.718, I think. And this you could type into a calculator, and you'll find, I think it's 5 point something, so it's actually less than 6. So we found our first upper bound. This is half of the result we're looking for. We're saying the sum of the inverse primes for p less than or equal to x is less than log x plus x. That means this is always less than that. Now, on its own, that isn't useful. It might look attractive. It might look like we found our answer of the form log x. But actually, if this is of some other weird form, which happens to be less than log x, if it's like -1 over x or something, it's always going to be less than that. So we need to know what the lower bound is as well. So let's use the other lambda L. There it is, and this time we're plugging it in. Let's look at the expression that we're using this time. We're saying the generalized sum using lambda L is less than the generalized sum using lambda naught, which we know is the interesting series. And this time we're saying that generalized sum is more than lambda 1 log x plus this bit here. We're using the more than part of this inequality. So it's more than log x plus the expressions here. And again, it's easy. Pop in the values for alpha and beta, and this turns up to be more than log x plus 3. So that's now a lower bound. So we've done it. We've actually found a lower bound and an upper bound for the prime harmonic series for p less than or equal to x. Phew. So it's easy to get lost in all that algebra, and the point of this video was to actually work through the algebra. But hopefully we saw the overall plan for what we were doing, which was to find an equivalent expression for this, and then similar ones that we could have a less than and a greater than inequality for. So we can finally say that the prime harmonic series, the partial sums, grow like log x. Phew. Now, the other proofs that I've found around in the textbooks and online require a lot more mathematics. So this one didn't require any advanced maths, as you can see. Nothing was particularly advanced. It just took a little bit more work. But we got there. Here's just a visualization of the this is an experimental kind of result. So the blue line here is plotting the 1 over p hump, the partial sum, and it goes up and flattens out, and you can see it looks logarithmic, but we know now that it's log n. N's going up to 1000 here, and the red one is actual log n. You can see the difference. In fact, the green line here is the difference, and it seems to be approaching a half, which is a stronger result than what we've proved. But remember, the experimental results are just pointers and hints. They're not valid proofs. So although our proved upper and lower bounds are good, they perhaps could be better. But I think they're very good as they are, because they've given us within a narrow range that the prime harmonic series grows in. And it's interesting that the prime harmonic series grows as log x. It means it grows really slowly. And here's just some examples. So x is 10, log x is 2.3, log x is 0.83, and as x gets bigger and bigger, this is a million, a billion, is that a trillion? I don't know, 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 10 to the 12. log x is still only 3. So log x grows really slowly. So that's interesting because the prime harmonic series grows very, very, very slowly and still diverges. Isn't that interesting? Fantastic. Well, I hope you found that useful. It was a lot of work, but this video is really aimed at anyone who wants to work through Paul Pollack's paper and finds that the proof presented there moves too quickly without explaining each step. That's what this video is about, and it's written up in the blog as well, because there's quite a lot to take in, so do have a look at the blog as well. It kind of writes things down. Well, I hope you enjoyed that. That's concluded a nice kind of phase in our learning, and I think in the future we'll start exploring some interesting things around the connection between the primes and the Riemann zeta function. We might even start exploring the prime number theorem and seeing how others have proved it. Yeah, fantastic. See you next time. Bye.